In last few lectures, we investigated propagation of an electromagnetic wave inside waveguiding structures. First, we investigated propagation inside what is called a parallel plane waveguide, and later we derived the fields inside a rectangular waveguide. Of course, the approach which we took in two cases was different. In first case, that is for parallel plane waveguide, we visualized the propagation of electromagnetic wave as the propagation of uniform plane wave by multiple reflections at the two conducting boundaries of the parallel plane waveguide. Whereas in case of rectangular waveguide, we took the mathematical approach, that is, we simply said if we wanted to have the transverse electric or transverse magnetic field, mathematically just solving the wave equation and satisfying boundary conditions, what kind of fields we would get. The visualization which we had in case of parallel plane waveguide gave us the physical understanding of what kind of field can exist inside a waveguiding structure, and from there only we understood that if we go perpendicular to the planes, the conducting boundaries, then we will have the wave which will be standing wave kind of waves, whereas along the planes we will have a travelling wave. And using this physical understanding, we can appropriately write the mathematical functions for electric and magnetic field inside a rectangular waveguide. So in one case we had physical visualization of the phenomena, in other case it was a purely mathematical approach, and now we must verify that mathematically, which we did blindly for rectangular waveguide, does it give me the fields which we have derived from the physical understanding for a parallel plane waveguide. So essentially what we have to do is, we have to establish that the fields which we got for rectangular waveguide, if we take the limiting case, then the fields must represent the fields which we got for the parallel plane waveguide. So now what we will do is, we will do an exercise of showing that these fields which we got for rectangular waveguides indeed represent the fields which we got for the parallel plane waveguide in the limiting case when one of the dimensions of the waveguide becomes infinity. And then we will also ask a question, what happened to the mode which was TM0 mode, which became the TEM mode in the parallel plane waveguide? What happened to that mode in the rectangular waveguide? Does that mode now exist inside rectangular waveguide, or it exists only inside the parallel plane waveguide? So let us take first the second question, that is, does the transverse electromagnetic mode exist inside a rectangular waveguide? This we can argue physically, that if we consider a rectangular waveguide, and let us say that we are talking whether transverse electromagnetic mode would exist inside the structure. That means for this mode, the electric and magnetic field both are perpendicular to direction of propagation. That means they must lie in this plane, the cross sectional plane, that is the plane of the paper. Now we know that the magnetic field lines must close on themselves, and all these magnetic field lines are now lying in this plane. That means they must form the closed loops in this plane. So the magnetic field lines in the transverse plane must look like that. However, if the magnetic field lines are like this, then we know that there has to be a current enclosed by these magnetic field lines. So there must be a current flow, something like this, which is enclosed by the magnetic field lines. Then and then only these magnetic field lines can survive. So there are two possibilities. One is we have a conduction current which is flowing perpendicular to plane of the paper, and that is enclosed by these magnetic field lines, so they can survive. Or there could be displacement current which will be perpendicular to the plane of the paper, and that will be enclosed by the magnetic field lines, so the magnetic field lines can survive. Since we do not have any conducting medium inside this waveguide, this waveguide is completely hollow, it means filled by pure dielectric, there is no possibility of conduction current enclosed by this magnetic field lines. So, that means the conduction current is 0 inside the rectangular waveguide. So, only possibility which can exist is we have a displacement current to support this magnetic field lines, and this displacement current must be flowing in that direction. But the displacement current would require the electric field which will be going in that direction, which we already denied for transverse electromagnetic mode. So, for transverse electromagnetic mode, we say the electric field also lies only in the transverse plane. That means it does not have a component perpendicular to the plane of the paper. If that is so, then we cannot have the displacement current inside this waveguide which is in this direction. So, neither we have conduction current flowing this way, nor we have displacement current flowing this way. So, there is no current which is flowing perpendicular to the plane of the paper, and if there is no current, there cannot be magnetic field lines, because by Ampere's law this magnetic field lines must be related to the current enclosed. So, that means these fields which are lying in the transverse plane, they cannot exist, because there is no current to support these magnetic field lines. That means this mode, the transverse electromagnetic mode, cannot exist inside a rectangular waveguide. So, this mode, TEM mode, does not exist inside this waveguide. Then one can ask a question, how was it existing in the waveguide which is the parallel plane waveguide? And before we get into that question, let us first take the parallel plane waveguide as a limiting case of the rectangular waveguide. So, if I take this rectangular waveguide in which the TE10 mode is existing, that means the electric field is like this, and if I make this B equal to infinity, if I push this wall to infinity, essentially I will get a structure which will be the parallel plane structure, this plane and this plane. Wave is going to travel in the z direction, and these two walls are pushed to infinity. So, as a limiting case of the rectangular waveguide, by pushing these two walls to infinity, I can get the fields for the parallel plane waveguide. And in this case, since the electric field is like this and the wave is going to propagate perpendicular to the plane of the paper, this mode essentially would correspond to the TE mode. So, we have now, by pushing this thing for TE10 mode, if I push this field walls to infinity, then I will get a geometry which will be the parallel plane geometry, and for this geometry electric field is oriented like this. So, that will give me the transverse electric mode. So, what we are saying is, if I take this waveguide and push it to infinity, so these are the two walls of the waveguide, this is my coordinate axis, this is the direction which is the z direction, this is the x direction, and I am pushing these two walls to infinity. And the electric field now is oriented in this direction, which is this way. So, I have a component which is Ey, and I have the magnetic field which is Hx and Hz for the TE10 case. So, if I look at the fields which I had for TE10, I had Ey component, I had Hx component, and I had Hz component, and these fields were constant as a function of y. Same thing we can get now for the infinitely extended waveguide in y direction. That means if there are no boundary conditions to apply in this direction, these fields are infinite, then this field is constant in that direction. That is precisely the field we used to get for parallel plane waveguide. So, indeed we can take the transverse electric 1-0 mode, make this boundary to go to infinity, but since we do not have any dependence of B here, what that means is these fields are the same fields as I would get inside a parallel plane waveguide for a transverse electric 1 mode. So, these fields are T10 for rectangular waveguide, but these exactly the same expression I have for TE1 mode for a parallel plane waveguide. So, we have a situation here which is TE1 mode, for which the fields are identical to these fields which are TE10 mode for the rectangular waveguide. So, here we have the magnetic fields which are having x component and z component, and Ey will be in this direction. So, you are having now the z magnetic field which is in this direction. So, as a limiting case of the TE10 mode, we can get the transverse electric mode, lowest order transverse electric mode, which is TE1 mode, and the fields will be exactly same as what we got for TE10. The another mode which we had was the transverse electromagnetic mode, for which the electric field was not tangential to the boundaries, it was perpendicular to the boundary. Magnetic field was tangential to the boundary, and we saw that was the mode which was non-dispersive and which travelled as if the conducting boundaries are not existing, and that is the mode which was the TEM mode. So, we had a situation that if I take a parallel plane waveguide like that, and if this is the electric field E and this is the magnetic field, H, then the wave is going to travel in this direction Z, and then this wave travels without any variation of electric and magnetic fields as we saw earlier, because neither H requires a boundary condition to be satisfied which is tangential. So, you can always have surface currents, nor the normal component of electric field needs any boundary condition to be satisfied, because you can always have the surface charges induced to compensate for the normal component of the electric field. So, this mode which was the transverse electromagnetic mode was existing inside, and now one can ask a question, if this was the limiting case of the rectangular waveguide, how come this mode exists in this, but when we take a rectangular waveguide this mode does not exist? One can argue that since the magnetic field is in this direction and since this plane is extended in y direction, one can say that these magnetic field lines essentially close at infinity, and they enclose these conductors, these conducting boundaries which have the current flowing on them, the surface currents. So, in the case of rectangular waveguide where these boundaries are finite, these magnetic field lines they have to close on themselves, and that is why the current is not enclosed. So, this mode cannot exist inside a rectangular waveguide, but if I take a parallel plane structure, then these magnetic field lines will close at infinity and they will enclose these conductors, and that is why this mode can exist inside the parallel plane waveguide. This is the mode which is, as we saw in case of two conductor system like a coaxial cable or transmission line, this mode propagates. So, whenever we have a two conductor system, the lowest mode which will propagate will be TEM mode. However, if you go to the rectangular waveguide, then the lowest mode which will propagate will be TE10 mode. So, we have a very important conclusion to draw, that whenever we have the hollow structure, hollow pipe kind of waveguide, the transverse electromagnetic mode cannot exist, which is non-dispersive, because this was a very special mode. This mode is not supported by the rectangular waveguide, and that is why we have all those problems of dispersion and so on inside a rectangular waveguide. But that is the structure which is more physically realizable structure. We should remember that. the parallel plane waveguide is still a structure which is infinite in extent. So, we cannot realize this in practice. It is good for understanding, but when we want to realize the structure in practice, it is the rectangular waveguide which can be realized in practice, not the parallel plane waveguide. So, whenever we have a physical structure which is rectangular waveguide, we will always have a cutoff frequency associated with that, and we will always have the problems like dispersion and so on associated with them. With this understanding, now let us try to see the currents which get excited on the walls of the waveguide, which actually support these fields inside the waveguide. So, whether we take a parallel plane waveguide or you take rectangular waveguide, what is the mechanism by which these fields are supported inside the waveguide? What are the sources? And the sources are nothing but the surface charges and surface currents which lie on the inner surface of the waveguide. So, as the wave travel, even the surface charges keep moving, they accumulate at different locations, as we will see little later, and these charges and surface current support the electric and magnetic fields inside the waveguide, which are responsible for carrying power inside the waveguiding structure. So, what we will do now, we will try to visualize first the fields which would be there inside the waveguide, and then we will try to visualize how the currents are distributed on the walls of the waveguide. So, let us take for the simplest case, which is the TEM case and a parallel plane waveguide. So, let us say I have a parallel plane geometry, and let me orient the planes. So, these are the two conducting planes. The energy is going to propagate in this direction, and if I take the TEM mode, we saw the TEM mode, the electric field is perpendicular to this. So, if I say this is my x direction, this is y direction, then we had the electric field E y, which was some constant e to the power minus j beta z, and we had a magnetic field which was H x, which is c upon eta e to the power minus j beta z. If I visualize these fields, so if I really want to find out how these fields are going to be as a function of space and time inside the structure, first what we do, we freeze the time. Remember, all these quantities are intrinsically functions of time, and they are having a harmonic variation as a function of time. So, e to the power plus j omega t is implicit in all these terms. So, as such, these fields are going to vary as a function of space and time. So, if I stand at particular location, the fields are going to vary sinusoidally as a function of time. If I freeze time, that means instantaneously look along the waveguide, I will see the field variation which will be given by that. So, essentially for what we do to visualize these fields in 3 dimension, first we do is freeze time, that means make this quantity constant, and then without losing generality we can say let make t equal to 0. So, at that instant I want to see how the fields are distributed in space, and once I get those field distribution in space, then we simply say that these fields will be moving with the velocity which is the phase velocity for the mode. So, then they let the field drift inside this waveguide with the phase velocity. So, when we visualize these fields, essentially we try to visualize the spatial variation of the field at some instant of time, and without losing generality we can take that time is equal to 0. So, if I take the t equal to 0, if I freeze time, then the field visualization will be simply a real part of this quantity, which is real part of c e to the power minus j beta z, and this will give me again the real part of C upon eta e to the power minus j beta z. So, Ey has a variation which is real part of this, which is C into cosine of beta z. Hx will be having the same variation, C upon eta cosine of beta z. So, if I consider this point as z equal to 0, this variation is beta z, and the wavelength which we have here, or the phase constant, is beta. So, the corresponding wavelength, let us call in general, that is the guided wavelength in the direction of the wave propagation. So, this field has a period, spatial period, which is equal to the guided wavelength, and at z equal to 0, this field is maximum. So, it is maximum here, and it is not varying as a function of x or y. So, the fields are constant everywhere. So, now the field is varying as a cosine function along the z direction. So, it is maximum here. So, if I take here this point, this is z equal to 0. So, it is maximum, and then it goes like that as I move along the z direction like a cosine function. Where this is 0, this quantity will be lambda g by 4, where this function will go to 0. If I go again lambda g by 4, this function will become negative, and so on. So, this field now I can visualize as the electric field which is constant everywhere. So, this is the field distribution for the electric field is like that, which is same everywhere, and so on. And the magnetic fields are horizontally oriented, and they are again having the same amplitude all across. So, this is the direction of the magnetic field. So, the direction is taken appropriately, so that E cross H gives me the power flow which is in this direction. So, this is the magnetic field which is everywhere distributed. So, this is my H vectors and this is my E vectors, and it is maximum here as I move to lambda g by 4 along the direction of wave propagation. These fields will go to 0, then again they will reverse the direction after lambda g by 4, go to maximum when z becomes equal to lambda g by 2, and so I got a variation which is, if I look like that, if I turn it, electric field is maximum here, slowly reduces, goes to 0, changes direction, again increases, maximum negative. So, start from here, goes to 0, change direction, increases, again maximum. That is the way the electric field is distributed. So, you can see as if there are rods here which are standing of different heights. It is maximum here at z equal to 0, the height of the rod goes to 0 at lambda g by 4, the direction of the rod is reversed, and again the amplitude becomes maximum when I go a distance of lambda g by 2. Same thing happens here for the magnetic field lines, which are now like that. So, they are stacked. So, this will look as if you are having a layer of the magnetic fields which are oriented this way, they are stacked, and again their variation will be exactly same, that when this field goes to 0, the magnetic field also will go to 0, and so on. So, it requires little imagination to really visualize these fields, but with little practice one can definitely see how the electric fields and magnetic field are distributed inside a waveguide. Now, we know that if the magnetic field is like that, the current which is going to flow on the surface of this conductor is related to the magnetic fields, tangential component of the magnetic field. The N cross H gives me the surface current on these conducting walls, and since we are considering here the ideal conductors, essentially if I calculate N cross H, that is the current which is truly confined to the surface of this parallel plane waveguide. So, if I consider this surface, then the normal will be coming outwards. So, this is my normal unit vector, whereas if I consider this plane, then the normal which will be coming out of the conducting surface will be this normal. So, the unit vector outward normal for the lower plane will be going upwards, the unit normal for the upper plane will be going downwards. And now you can calculate n cross h everywhere. So, this is the direction of h, this is n. So, if I calculate n cross h at that point, I will get the direction of the surface current, which will be along the direction of the wave propagation. Similarly, so on this surface the current will be going in this direction, because I get n cross h, whereas if I go to this surface, then I will get n cross h, n is now downwards, h is this. So, I will require n cross h, which gives me the current which will be coming out. So, on the lower surface I get a current which is going this way, this is my surface current, whereas on this surface the current will be flowing this way, which is Js, and it will be having the same variation as the variation of the magnetic field. That means it will be a maximum here, after a distance of lambda g by 4 this current will go to 0 and so on. So, in a two conductor system, it gives you the current flow in the direction in which the wave is propagating. I have a current flowing this way, I have a current flowing this way, and precisely that is what essentially we are used to, that when we have a two conductor system like a coaxial cable, we connect a voltage source and the current goes inside the conductor, the current returns by what is called a ground path. So, we see that the current goes inside from one terminal and current comes outside from the other terminal. So, in that situation, which is like a two conductor system, the direction of the current flow which we have for this mode, TEM mode, keep that in mind, is same as the direction of the wave propagation. So, the current is going, current is returning from here. Question one can ask is, if the wave is propagating in this direction, is it always true that the current has to flow in the direction of the wave propagation? And invariably we get the answer which is wrong, and that is, since we always discuss the transverse electromagnetic mode, that is what we are used to when we go to low frequency circuit, immediately we jump to the conclusion that yes, since the wave is moving in this direction, the power is flowing in this direction, the current must flow in that direction. Let us look at the parallel plane waveguide, but let us take the mode which is TE1 mode, and let us see what will be the direction of the currents and field in that waveguide. So, let us consider the structure which we had got. This is the TE1 mode and this is the parallel plane waveguide. As we saw that the fields for the parallel plane waveguide will be identical to this. So, firstly the electric field will be y oriented, they will have variation which will be in x direction, and they will be varying again in z direction with phase constant beta. So, in this direction if I look at the field variation and if I write down the expression for this, I will get again sinusoidal variation in z direction also. However, to visualize these fields as we did in the previous case, let us take amplitude of this field, that is the real part of this quantity, and plot that as a function of z, x and y. We will get a three-dimensional picture of the fields. Before we do that, however, let us try to take this j and represent that along with this, because j is e to the power j pi by 2. So, minus j will be e to the power minus j pi by 2. So, if I take this field expression and write that, I get this quantity E y, that is equal to, let me put this whole quantity as some constant at the moment we are only interested in finding the variation of the field in x and y. So, let there be this some constant here, except this j we are going to put at this point. So, let us say I have some constant here, some a, sine of pi x by a, and I write here e to the power minus j beta z, and I take this minus j up. So, this will be equal to minus j pi by 2. So, if I want to get the instantaneous field as a function of x, y, z, I take real part of this quantity. So, the instantaneous value, the electric field, that will be real part of E y, that will be amplitude A, sine of pi x by A, cosine of this quantity, and that will be equal to the sine of beta times z, because you have a phase difference here of pi by 2. So, you have here sine of beta into z. Which we can write down explicitly in terms of the guided wavelength. So, this we can get as a sine of pi x upon a sine of 2 pi by lambda g into z. Same thing I can do for this magnetic field also. So, this quantity again, with there is omega epsilon, this is omega mu. So, I can say this is another constant for the magnetic field. So, H x I can write down the instantaneous value, that will be real part of H x, which will be some constant b sine of pi x upon a, and this quantity is same, again we can take here minus j up there. So, this will be sine of 2 pi by lambda g into z, and I can get again the instantaneous value for the magnetic field z component, and there is no j here now. So, if I take real part of this, this will be simply cosine of beta z. So, the real part of the z, that will be equal to this constant c cos of pi x upon a cos of beta z, which is 2 pi by lambda g into z. So, these are the fields which are now, if I freeze time and if I take that t equal to 0, then at that instant the field along the waveguide will be given by this expression. So, in the z direction, as we can see, the fields are sinusoidal with a period, spatial period, which is lambda g. However, these two are in quadrature, that means wherever h x is maximum, the h z is 0, and wherever h z is maximum, h x will be 0. So, in space we are having two components now, the h x component and the h z component, and h x component is having a sign variation. So, if I take this point as z equal to 0, h x is 0 at this location, but h z is maximum at this location. If I go a distance of lambda g by 4 on this, at that location h x will be maximum, but the h z will go to 0. So, if I see from the top, it will appear here the Hx was 0, only Hz was here. As we moved to a distance of lambda g by 4, the Hz becomes 0, only Hx became maximum. So, the magnetic field totally became like this along this direction. As I move further by again lambda g by 4, again Hz will become maximum, Hx will become 0. So, what we find that here we have a function which is cosine. So, that means if I take this as plus direction, so here I have a magnetic field like that. On the opposite wall, the magnetic field will be this way, this is the cosine function. So, z equal to this quantity, this variation as a function of x. So, if I plot this, this is the one which in the x direction is going to be like this. Z direction, the variation is periodic with lambda g, but in x direction this is maximum at x equal to 0, at x equal to a with opposite sign, and 0 at the center. So, the magnetic field lines are maximum here and no component of the magnetic field Hx at this location. So, the fields are this. If I go to a distance of lambda g by 4, in this direction, at that location, if I see here, the Hz would go to 0, Hx will be maximum, but the Hx is having a variation of sine of pi x upon a. That means Hx is maximum at this location, but it is not maximum on the walls. This function is a sine function. So, it is 0 here, 0 here, and will be maximum here, and that will be the direction for Hx, which will be like that. So, if I see from the top, I see situation like this for the parallel plane waveguide. So, if I am seeing from the top like that, the magnetic field, this is z equal to 0. The magnetic fields are like that here. When I go to a distance of lambda g by 4, this thing has gone to 0 and Hx has become maximum, but so that is oriented in this direction. Now, it is a matter of little imagination. Since we know that the magnetic field lines close on themselves, essentially we have a magnetic field loop which is created like this. So, we got the magnetic field lines which will go like that. Like this. If I go further lambda g by 4 from here, the direction will be reversed. So, if I go further in this direction, this direction is x, remember. So, again I get the magnetic loop which will be like this, and so on. If I complete this, if I now say that I have a waveguide which is running from minus infinity to infinity, essentially I will get the loops of the magnetic field lines which will look like that, where this separation will be equal to lambda g by 2. So, if I look at the waveguide which will look like that, this is a parallel plane waveguide. The magnetic field lines look like rolled carpets which are stacked inside the structure, and they are of infinite length which are perpendicular to the plane of the paper. That is the way the magnetic field lines will be distributed. What about the electric field? The electric field has a variation in z direction which is same as this, but it is oriented in y direction. So, if I consider in this, it is having a sinusoidal variation in this direction, but oriented this way. So, if I see from the top, then the electric field lines now will be perpendicular to the plane of the paper, and behavior of this Ey and Hx is identical. That means, wherever Hx is maximum, Ey is going to be maximum. Only thing, it has a variation which is sinusoidal variation. So, it has identical variation to Hx. So, if I look at the Hx component, which is this component, here is the Hx component which is maximum. So, the electric field also will be maximum at this location, but electric field is always oriented in y direction. So, I have the electric field which will be like that, and if this is the direction, positive direction for z in which the wave is propagating, again you can have E cross H. So, if this is the direction of the magnetic field, the electric field should be going inwards. So, E cross H gives me the Poynting vector. So, that is the direction of the electric field, and this electric field reduces to 0 at this location. So, I have electric field becoming lesser and lesser as I go this direction. Similarly, it is becoming lesser and lesser because tangential component should become 0. So, this becomes less here, and so on. Again, wherever I go on this side, the electric field now will be coming outwards, amplitude will increase again. So, here the size of the circle tells me the strength of the electric field. So, the electric field will be distributed maximum where the Hx component is maximum. So, this is more like rods which are inserted in these rolled carpets, that is the electric field vectors. So, if I want to visualize in the 3-dimensional kind of fields, the electric field will be the stacking of the rods of different diameters, where the diameter represents the strength of the electric field, and the magnetic field will be like stacked rolled carpets, which will be like that. Once we get this magnetic field things, which is now a rolled carpet which we have got, which you have seen from the top, so magnetic field lines are like that. Now, we can ask what kind of currents are going to flow in this. So, as we know, the currents will be related to the tangential component of the magnetic field on the walls, and the tangential component of magnetic field, which is this on this wall, these two walls, is only z component. On this wall there is no x component. So, on this wall the unit normal will be going inwards. So, this is my n. For this wall, this is n. Here the magnetic field is going tangential to this, which is in this direction, z direction. X direction magnetic field is 0. So, on the walls, if I see, I have only magnetic field component which is z component. So, if I calculate n cross h, this is n and this is h. So, if I go from here to here, the n cross h in this direction, I will get now the current direction, which will be tangential to this surface current. That is what we are talking about, but that will be now flowing in the y direction, because normal is in x direction and the magnetic field is in z direction. So, n cross h, if we take, that current flows in the y direction, which is this direction. So, we have now the surface current which flows into this. So, if I take again, this is my unit vector, this is my magnetic field which is like that. Okay. I take n cross h, which will be going from this to this. I get the direction of the current, which will be surface current, which will be like this. This is Js, like this is Js. So, very important thing to note now is, compared to the TEM case, that the surface current is going to flow in the y direction. That is very important. So, we have here surface current in y direction. Again, it will have a variation which is sinusoidal in z direction, but there is no current flow in z direction. That is the important thing to note. But the wave is travelling in z direction. If the wave is travelling in z direction, the power is flowing in z direction. So, what we now find something very interesting, that the power flow, there is no component of current, surface current in this two conductor system in the direction of the net power flow. The current flows in this direction, but the power flows in this direction. So, the notion which we have at low frequencies, that since the power is going inside the system, the current must be flowing in the same direction, that is completely wrong. In fact, the direction of current flow and power flow have nothing to do with each other. The current may flow in some arbitrary direction and the power may flow in some other direction. In fact, it will be also immediately clear to us that where is the power flowing, where is power? The ideal conductor does not carry any power inside. The power is only between these two conductors. So, the power is carried by the fields which are trapped between the conductors, that is what is carrying power. To support this field we require the currents. So, the currents are not carrying power, the power is carried by the fields. So, there is no reason why the current should flow in the same direction in which the power is flowing. However, as I mentioned, at low frequencies we normally have a wrong notion that since the power is flowing inside the circuit, the power is carried by the current, the power is carried by the charges. So, we get a wrong picture that the currents have to flow because the current is going to carry power. In fact, this is now a better understanding which says that power flow is because of the fields and not because of the currents. So, the current may flow in some arbitrary direction, and in this case you can see it actually flows perpendicular to the direction of the power flow. So, the power flow in z direction and the current flows on the surface of these two conductors, which is in this direction. So, the notions normally which we have at low frequency circuits, they come from the transverse electromagnetic wave, though we do not say that explicitly there, because that time when we talk about the simple circuits, we do not get into the complications of the field distributions. But intrinsically we assume that the fields which are carried by the electrical circuit is a transverse electromagnetic field. So, we have certain notions which we build for the electrical circuit, and they come essentially from the nature of transverse electromagnetic wave. As soon as you make a departure from the transverse electromagnetic wave to a transverse electric or transverse magnetic case, then all those notions completely break down, and then we get much global picture of propagation of electromagnetic waves and the currents and the distribution of charges and so on for various configurations. So, with this understanding now for the current flow on this parallel plane structure, which is rather simpler structure, now we can discuss the field distribution inside the rectangular waveguide, which is more practically a realizable structure. And then again we will see the current flow on the waveguide surface for rectangular waveguide, and then we will have a little more advanced things like calculation of the losses and other things for rectangular waveguide. So, let me summarize what has been discussed here. Essentially we saw that the transverse electromagnetic mode cannot exist inside a rectangular waveguide, and that we showed from the physical arguments. Then we also showed that if we take a rectangular waveguide and push one of its dimension to infinity, then the fields which we get for rectangular waveguide, they are identical to what we would have got for parallel plane waveguide. Then we developed a mechanism of really visualizing these fields inside these waveguides. So, we saw two cases. One was the transverse electromagnetic wave inside a parallel plane waveguide, other was TE1 mode inside a parallel plane waveguide. And then we saw something interesting, that the direction of the current flow on the surface of the waveguide need not be same as the direction of the power flow. The direction of the current and the power flow are same for only transverse electromagnetic case. However, if we go to general mode, then the current might be flowing in different directions, and the power flow which is due to the fields trapped between the two conducting boundaries could be in some other direction. So, next time we discuss in detail the fields and the power flow inside a rectangular waveguide.